we have a lot to say about problem number 6, this next page. And here's what it is. It's because in order to see if a series is going to converge or not for a particular value of x, well, you need to plug in that number for x. And then there's kind of a lot to say. So you can read over this, and let's just explore a little bit more. So once again, what they're saying is if we wanted to know if this converges for x is equal to 2, we'd plug in 2 for x. And notice what they give us is doing the math, we're going to get 2/3 to the n times 1 over 2 to the n. And really our point of reference is geometric series. We know that for a geometric series, this will converge if our r value is less than 1. So this, had we gotten rid of the 1 over 2n, we would be left with a geometric series that definitely converges. In other words, the terms that we add on every single time are sufficiently small to ensure that this is going to converge. But then we're taking that converging series, and for each term, we're multiplying it by something, in fact, that's going to be less than 1, which makes the terms even smaller. So because what we have is something that is unknown, but we know that it's even smaller term by term than a converging geometric series, we can say that this is going to converge for x is equal to 2 as well. So now let's try that with something else. So let's see what happens. Let's see if we can make this even bigger. What happens if, let's go up to x is equal to 3. Well, instead of, so once again, what we started with was x to the n minus 1 over n times 3 to the n. So instead of x, we're going to have a 3 in there. And still goes between from 1 to infinity. And here's what I'm going to do. I'm going to rearrange this a little bit. I'm just going to use algebra. I'm going to write the top as 3 to the n times 3 to the negative 1 over n times 3 to the n. And our 3 to the n's cancel out. So now we're just left with the series, and goes between 1 and infinity, and we're just going to have 1 over 3n. And we know from our rules of series that we can take out that 1/3. So we're just taking 1/3 of, in fact, the harmonic series. And we need to pause and talk about something, because we talked about a proof as to why the harmonic series is going to diverge. And the proof was that ancient proof where you show that every term is going to be greater than a power of 1/2. And so that's one reason why this is going to diverge. Here's something else, and this is important. This is important, and it refers back to something called the integral test. And the integral test you don't know, but it makes perfect sense. What you do know is that if we are taking the function between 1 and infinity of 1 over x, well, we talked about this earlier. That's really the limit as b approaches infinity. And when we take the antiderivative of 1 over x, we get ln x. So ln x between 1 and b, which is going to give us the limit as b approaches infinity of ln b minus ln 1. But as b approaches infinity, ln b also goes to infinity. So this integral will diverge, is what we would say. Let's look at how that compares to the harmonic series. For the harmonic series, I could consider that I am taking rectangles. And for each rectangle, this is the height. The width of each rectangle is 1. And for example, the width of my first rectangle is going to be 1. Well, the height of 1 over x, when x is equal to 1, is 1. So 1 is the area of that rectangle. The area of my next rectangle, my height is 1/2, and the width is 1. So 1/2 is the area of the next rectangle. 1/3 is the area of the next rectangle. 1/4 is the area of the next rectangle. So I could look at the sum of all of these rectangles and see that the area of the sum is greater than the area under this curve, which we already know goes to infinity. So because of the integral test, because this diverges, and in fact I know my sum of rectangles is going to be greater than this, then I know that the harmonic series also diverges. And one thing we talked about with integrals was this. Anytime you are taking the antiderivative of 1 over x to some p-value, we had said that this diverges or converges based on the value of p. So in fact, if p is greater than 1, this is going to converge. If p is less than or equal to 1, this is going to diverge. So sometimes we call this the p-series. And in fact, with our summation, we can talk about the same thing. Basically, we're using the integral test. Whoops, I meant n to the p. As n goes from 1 to infinity, that we know this is going to then converge, again, if p is greater than 1, but diverge if p is less than or equal to 1. And again, we can use the integral test to come back. So let's go back to where we were. We were looking for, does 1 over 3n diverge or converge? Well, we know that if we're going to take the antiderivative of 1 over 3x dx, this is going to diverge. And so we know that this sum will diverge as well.